But yeah, so in section 9.7a, we're trying to figure out, like, can I write sine of x as a polynomial? Okay, can I write e to the x as a polynomial and get a good representation of this stuff? Okay, and that's one of the things that they were doing many years ago, because they didn't have the ability to get these graphs on graphing calculators. They basically would approximate what a sine of x function would be. What would a cosine of x function be at a certain point? They would use polynomials to do the calculations. They wouldn't just use a graphing calculator, right? So let me see why this is glowing here. I don't know why that's glowing, but there we go. So anyway, to approximate an elementary function, we're going to do the following. So let me write this down right here. To find a polynomial approximation of an elementary function, we're going to do the following. So number one, and right now I'll show you an example so you can see how this looks. We're going to find a polynomial function p and function f and a number c such that p of c is equal to f of c. Okay, this is called being centered at c. So let me put this right here. This is called being centered at c. So being centered at c. So if you see like f of -1, that means you're centered at -1. If you see f of 3, you're centered at 3. Okay? So you're going to find a polynomial function p and function f at a number c such that p of c is equal to f of c. So we're going to say that we're being centered at c. Sometimes they call it being expanded at c, but most of the time people will mention it as being centered. Okay? Your second step, ensure that the slope of p is the same as the slope of f. So is the same as the slope of f at c. In other words, p prime of c is equal to f prime of c. Okay, so this is how we do the process. I know it doesn't seem to make a lot of sense. Let me just kind of give you an example, and then hopefully it makes more sense from there. Go ahead.
So c is always going to be the same number?
Yeah, we're always going to be centered at a specific number. Well, we call these Taylor approximations. If the center is at 0, then it's called a Maclaurin approximation. But if it's centered anywhere else, then we call it a Taylor one. And we're actually going to talk about the definition later, but for now, we're not supposed to know, right? It's supposed to be a mystery. But let me show you an example real quick of how this works, okay? Because I know when you look at that how-to, it doesn't seem to make a lot of sense. You're thinking, like, what are they talking about? But let me give you an example so you can kind of see it. So for the function f of x equal to e to the x. Now, this is called an elementary function. Whenever in math we say the word elementary, it usually means hard, okay? Even though it's supposed to be easy, but usually the functions aren't very elementary, right? They seem to be more high school. But that's the word that they use, elementary. So for the function f of x equal to e to the x, find a first degree polynomial. So we're trying to do an easy problem here. First degree polynomial find a first degree polynomial function, And they're going to give it to us here. P sub 1 of x equal to a sub 0 plus a sub 1 x, whose value and slope agree with the value and slope of f at c equal to 0, or sorry, at x equal to 0. Now, x equal to 0, that's actually my center. I know c is that value that goes there, but remember, c is just a number, right? So normally we write like f of x or p of x for a polynomial. So our center is at 0, right? So let me kind of highlight this really quick. So this is going to be our center.
So that's a sub 0, right?
Yeah, a sub 0. So a sub 0, a sub 1. So they're saying use the function f of x and find a polynomial expression, which they give us, p sub 1 of x equal to a sub 0 plus a sub 1 x, that will approximate the values of e to the x. Okay, so we're about to create a polynomial that's going to approximate the values of e to the x, but that polynomial I create is only going to be a first degree polynomial. Okay, so it's going to have just a power of 1 on the x at the most. Okay, the higher degrees you go into, the better the approximation. So you're about to see how bad of an approximation this is, but it's not always bad. We'll kind of check it out on Desmos just so you can check it out. Okay, so we're gonna find the function f of x equal to e to the x and its first degree polynomial, whose value and slope of that polynomial right there, the value and slope at 0 will be the same as the value and slope of f. Okay, so this is basically what they're saying. They say, all right, what we want you to do is we're going to get our original function, f of x equal to e to the x, and we're going to take the derivative of it because we need the slope of it. Well, the derivative is e to the x, so good, no big surprise there. Now they say figure out the value of f of x at 0 and the value of the slope of f of x at 0. Okay, so in other words, what's f of 0? And what's f prime of 0? Right, so that would be e to the 0, which is 1. And that's e to the 0, which is 1. So, okay, I'm not really surprised. So far, the work doesn't seem that difficult. I'm just getting my original function, I'm taking its derivative, and I'm plugging in 0 into both. What I just did right now is this part right here. Actually, let me not use that color. The value and slope of f. Okay, that's what I just did right now. The value and slope of f. So that's this. So, now that I've done that, okay, then I'm going to figure out the top part, this top part where they say make sure that the value and slope of p agree with the value and slope of f. Now I'm going to do that part. So, I know p sub 1 of x, right? I already know p sub 1 of x. Let me write that down here. So p sub 1 of x is equal to a sub 0 plus a sub 1 x. Well, what's the value of p sub 1 of 0? P sub 1 of 0 is a sub 0 plus a sub 1 times 0. So p sub 1 of 0 is a sub 0. Now let's take our derivative of this function, bless you. So let's do p sub 1 prime of x. What's p sub 1 prime of x? Just a sub 1. Because a sub 0 is just a number, that's going to go to 0. So if you take a derivative of a sub 1x, it's just a sub 1. So what's p sub 1 prime of 0? Well, is there an x where I can plug in a value of 0 to that derivative? No, so then that means it's just a sub 1. Now let's read again the very beginning where they said, like the very, very beginning, to do this, I want to set the original function equal to the polynomial function at the same point. And then I want to set the derivatives of each one of those equal to each other. So let's go back down. All right. They want me to get p sub 1 of 0 and set it equal to f of 0. They also want me to get p sub 1 prime of 0 and set it equal to f prime of 0. Okay, now why are they going to want us to do that? Well, let's do it and let's find out what the purpose of this is. So p sub 1 of 0 is a sub 0, right? I got that from this area right here. P sub 1 of 0 is a sub 0. What's f of 0? It's 1. So what I just found out is that a sub 0 is equal to 1. Okay? Now what's p sub 1 prime of 0? A sub 1. And what's f prime of 0? 1. So now I just found out that a sub 1 is also equal to 1. So let me write out my formula. P sub 1 of x is 1 plus 1x, or P sub 1 of x is 1 plus x. Now, this is supposed to be an approximation of e to the x. Do you think that's a good approximation? No, right? It's pretty bad. Now, let's kind of look really quick. This was a previous example. I know, pretty cool, huh? So 1 plus x. Oops, I pressed the wrong button. And then here, let me turn this off. E to the x. Where's the power thing? So would you say that that's a good approximation of that function? Right? Look right here. This point at negative 10, look at where it is over here. Right? They're not even close. But could you say that they're a good approximation, like right in between, like negative 1 to 1 maybe? That would be a decent approximation for negative 1 to 1, maybe negative half to half. It would be a decent approximation, right? But everywhere else, you don't want to use this to approximate, right? So what they decided to do when they were figuring out this part of the math for Taylor was trying to figure out, was saying, okay, this is a bad approximation. How can I make it better? Well, he said, well, what if I like got that function and maybe I added like a second power to it. Maybe if I got like something like this, instead of making it a first degree polynomial, let me make it a second degree polynomial. Is that a good approximation for it? I mean, look at the two graphs. Look at the green line and the blue line. Don't they look pretty good on the right side? Yeah. But then on the left side, well, that sucks. Right? On the left side, it's not very good. So he said, well, what if I make it cubic? Is it going to look better? Yeah, it will. What if I make it quartic? Right? What if I make this like a fourth power? Now, I don't know what's going to happen right now, so let's find out, though. Power of 4. So no, maybe if I need a square term in there, so let me put in a square term there, right? And the more I mess with it, and the more degrees I start putting into it, what you're going to notice is it starts to mimic the graph more and more and more. Okay. And right now you might say, well, yeah, right now you're messing with it and it doesn't look that much better. Well, it's because I'm not actually finding every term. There's a lot of terms I'm missing. But the idea is this. They started realizing that the higher the degree that they go to approximate the function. So in other words, if he were to make a 12th degree polynomial, it would fit that function a lot better. Okay? So, and this is what they had to do before because they didn't have what we have, where we can just kind of see it, right? So they had to approximate e to the x. That's why for all these values of e to the x, they used to make tables because they're like, well, this is what it is. That way they don't have to do all this extra work, right? So he figured, well, what I got to do is make sure I get more and more terms. The more terms I have, the better it fits, right? Because if I make it just look like this, right? If I just make it look like that, that's pretty terrible. I don't want to base my work on an approximation of e to the x that looks like a linear function, right? So this is why Taylor created this process, okay? He said, I got to be able to find a way to represent these really hard functions in elementary ways, okay, in polynomial ways. So that's what he did. That was his first attempt, I guess you could say. Now, what if we wanted a second degree? Okay, so I kind of showed you, but here's a question. Second example. What if we created a second degree polynomial using the following? P sub 1 of x equals a sub 0 plus a sub 1x plus a sub 2x squared. And f of x equal to e to the x. Okay? At x equal to 0. So basically, using the same information we just did, what if we went one more step? Because that first approximation was pretty terrible, right? A linear function to represent an exponential, yeah, it might work within negative half to half. You'll get some decent numbers, but after that, it's just going to be bad. Okay, exponential grows fast. Linear does not. Linear grows uniformly, right? So let's try to do the second degree. So P sub 1 of 0, we found this out. If we plug in a 0, P sub 1 of 0 is a sub 0, right? That would be my original function for that polynomial. And f of 0 would just be e to the 0, which is 1. Now, what's f prime of 0? Well, we figured that out earlier. That's still e to the 0, which is 1. And they want us to go second degree. That means I got to do second derivative. So the second derivative at 0, that's still going to be e to the 0. So that's 1. All right. Don't worry. They're not all a sub 1, a sub 2 is not 1, all of them. A sub 1 will be 1. We saw that earlier, right? When we did p prime sub 1 of 0, we got a sub 1, right? That's from the previous work. What we didn't do was a second derivative. So let's do that. I'm going to move it down here. So p sub 1 of x, which is a sub 0 plus a sub 1x plus a sub 2x squared. If I take the first derivative, I get a sub 1 plus 2 a sub 2 x. Are you guys with me on that? Okay, now notice if I plug in a 0 into that first derivative, I just get a sub 1, correct? Because 2a sub 2 times 0 is just 0, so I would just get a sub 1. So that's done. Let's take the second derivative. And actually, you know what? Do me a favor, guys. I just realized I'm not marking this right. Do you see how I put p sub 1x up on the top? It should be p sub 2. The base number tells you what degree. So let me change it on all the p subs. So p sub 2, because that's what we're trying to figure out, p sub 2, the second degree polynomial. So sorry about that. So we take our second derivative, a sub 1 goes away, what's left over? 2a sub 2. So what's p double prime of 0 for the second degree polynomial? If you plug in a 0, you get 2a sub 2. Remember, the definition says that these must be set equal to each other. These must be set equal to each other. And these must be set equal to each other in order to solve. So, a sub 1 is, a sub 0 is 1. A sub 1 is 1. What's a sub 2? Nope. So a sub 2 is right here. It's half, right? A sub 2 is half. And the reason is because 2a sub 2 has to equal to 1, which implies that a sub 2 must be half. Maybe I'll erase that and I'll put it like this. All right? So now that I know my values, I can just write my formula. P sub 2 of x is equal to 1 plus x plus half x squared. And if I look at Desmos, and let me put one more function here. So 1 plus x plus 0.5, that's my half. I guess I could do a half. I think it lets me. Half x squared. So look at the two functions. Okay? If you look at the two functions, obviously the green one is my e to the x function. Okay, that's the right function. My blue one is the first degree approximation. Okay? My purple one is my second degree approximation. So you might have said that the blue one looks pretty accurate from -half to half. But could you say that the purple one looks pretty accurate from -1 to maybe 2? Right? From maybe -1 to 2, you might say like, yeah, it's not too bad. It's not too far off. Okay? So notice how my domain of accuracy is growing. And if I do a third power, okay, then it's going to get even better. Okay? And I'm not going to do that, but if I were to do something with the third power, let's see, 1 plus x plus half x, and we'll go half x squared. Oops, wait a minute. It's in the wrong place. I really hate this keyboard. Hold on, let me put my keyboard on, because this annoys me. I hope they fix it for tablet soon, because that's really annoying. So we'll move this here. And then we'll just do like addition of a cubic. So so check it out. Let me get rid of the other pictures, okay? Would you say that that cubic looks pretty darn good from -1? Sheesh, I don't even know how far. I mean, it's pretty close, right? And if I do a fourth power, it's going to be even closer. Okay? So, I can put in a fourth power here. I'm just doing this because I know the pattern of it, okay? Now, maybe it's not that accurate to the left, but it's getting really a lot better towards the right, right? And if you do a fifth, a sixth, a seventh, you start getting way more accuracy, okay? So that's the idea of Taylor's stuff, okay? let me stop it there.